All right, so today we're going to continue our discussion of maps of the sphere onto the plane. And what I want to talk about today is cylindrical projection, which is probably going to be a little more familiar to you than the gnomic projection, which we did the other day. So I've drawn a sphere already, and cylindrical projection is going to map this sphere onto a cylinder, which we know already cylinder locally looks like Euclidean space. And so then you can unroll that cylinder and, and get a map from the sphere to part of the plane. So the cylinder, oops, sorry, move this cylinder onto here, about like that. So there's the cylinder. And the way we're going to do this projection is as if you're shining a light source from the z-axis here. So from here, you're shining your light out through the sphere onto the cylinder. So, so let's say I have a point right here on the sphere. I look at whatever height that point's at, and I shine, I draw a line through that point from the same height on the z-axis, and then I continue until it hits the cylinder, and that's my map. So the cylindrical projection projects out from the z-axis. In other words, from the line connecting the North and South Pole. Keeping the height constant. Then going on to the cylinder. And like I said before, we can always then cut the cylinder to oops, sorry. We can always cut the cylinder and then get a map to the plane. And the kind of surprising fact, which you're going to prove about this projection, is that it preserves area. Which is, again, it's a really nice property to have in a map. So the area of South America on the map is exactly, well, in this case, it's exactly equal to the area of South America on the sphere. Of course, I guess, in general, you would, once you unrolled this paper, you would shrink it to a manageable size. So in general, if our map is smaller than the size of the actual Earth, the area is proportional on the map to the actual area. But this projection preserves area. So that's what we're going to try to prove today. And the way we're going to do this is we're going to draw a little rectangle on the sphere. So I should add in here, we're going to be drawing a really small rectangle on the sphere. And then we're going to map it to the cylinder. And check that the area hasn't changed. Okay. Couple things to note here. So I put rectangle in quotations here, right? And the reason for that is on the spheres, it's not going to be an honest rectangle. It's going to be something that is not quite a rectangle, but is sort of approximately close to a rectangle. And so what we're going to actually prove is that it approximately preserves area. And the smaller your rectangle, the closer that approximation will be to the actual value. And then using some calculus tricks, one can argue that, you know, if it's approximately true and it's getting closer and closer to being actually true for smaller and smaller rectangles, then infinitesimally it must be true. And so, you know, doing some surface integrals in this case, you can argue that area actually is preserved via this map. But we're just going to prove the approximation this time. So what do I mean by a rectangle in quotations on the sphere? Well, I'm going to just create a four-sided figure that's bounded by longitude lines and latitude lines. So here's two longitude lines. Those are going to be the two sides of my rectangle. And I choose two latitude lines as well. Something like that. And then my rectangle is this region in here. Okay, and you know it's not quite a rectangle. It's not even a spherical rectangle because these red lines are not geodesics. But it's something that if I zoom in really far and I choose my latitude lines and longitude lines really close together, is a very good approximation of a rectangle. Okay, and then how do we project this? Well, we go out until we hit the sphere. And so what we get on the sphere, the top and bottom have constant height, and these longitude lines project to vertical lines on the sphere. And so we get something which, sorry, on the cylinder. So we get something on the cylinder which is actually a rectangle because both the top and bottom and left and right sides are actually geodesics. So that's what the projection is going to look like. And you notice right away that this map that we're doing, it definitely distorts things, right? I think you can convince yourself pretty easily that the red sides of the spherical rectangle get larger when I project to the cylinder. And you can check as well that the left and right, the blue sides, get smaller. So there is distortion here. And so it should be even more surprising that area is preserved in this picture. However, it turns out what we're going to show is that the distortion, which expands the top and bottom sides and decreases the left and right sides, it does the expansion and the decrease in the exact correct way so that the total area is in fact preserved. Okay. One other thing we're going to need in this picture, how much distortion of the various sides occurs depends on kind of what latitude we're at. So I'm going to draw this line here, this line here. Let's say this angle is theta. Okay. And so, I mean, of course, there's a slightly higher angle to get here, but let's assume that that this angle is really small compared to theta, and so we're going to again have an approximation that both of these angles are more or less equal to theta. Okay. I guess the other thing we're going to need is we're going to need to know the radius of the sphere. So let's say the sphere has radius capital R. Okay, and maybe I should have kept part of that picture. So, we're projecting out and we're getting this rectangle on the cylinder that looks like that. Okay. Now, how on earth are we going to show that the area of the spherical rectangle is equal to the area of the cylindrical rectangle? Well, what we need to do is see exactly how the red lines change and how the blue lines change under this projection map. And we can deal with those sort of one at a time. Now, as you might imagine, okay, this picture is getting kind of complicated, so we can simplify our lives by looking at different cross sections of this picture piece by piece. And as you might imagine, if you want to study what happens to the blue sides of the rectangle, then a vertical cross section is going to be the most useful. In particular, I want to sort of cut this picture with a plane that goes through that goes through like this longitude, or this longitude line here. On the other hand, if I want to see what happens to the red sides of the rectangle, I can do a horizontal cross section through one of these latitude lines right here. Okay, so let's do the vertical cross section first. So I'm going to cut it exactly at that first leftmost blue longitude line with a plane that goes through that line as well as through the vertical line connecting the North and South Pole. And so on that plane, this picture looks a little simpler. So this is the vertical cross section. My sphere looks like a circle, and my cylinder, when I cut it, I can do better. When I cut it, it just looks like two vertical lines. And whereas the rectangle in this picture, well, one side of the rectangle, the blue side, looks like that. And let's label our theta here. So this is theta, this is r. Actually, sorry, so I think it's going to be easier if we assume this angle's theta. And like I said, since this blue edge here is really small compared to the size of our sphere, and we're only measuring an approximation anyway, it doesn't really hurt to choose either of these angles to be theta. Okay. Actually, I do want this here too. Okay, so let's see here. So if I look at the projection, remember I'm projecting straight through from the center axis of the sphere. And so this blue curve is going to get projected to this little bit right here. Okay, and so you can see that the length of this blue line shrinks under this projection. Okay, and so let's say that this has length A, and then the new length, the projection of A, we'll call that C of A for cylindrical projection. Okay. And so the goal here is to calculate what C of A is in terms of A. It's going to depend on A, of course. It will depend on theta, as you can kind of imagine, because if you look at this, the distortion is much smaller if theta is close to 0, and it's much larger if theta is close to pi over 2. So we're going to calculate C of A. Our formula is going to depend on A, theta, and also the radius, potentially. These are sort of all the things in our picture. Okay, so my hint to you in trying to solve this problem is notice that I can move this vertical blue line here over to the left to get two sides of, well, I want to say a triangle. It's not quite a triangle because this curve on the sphere is extrinsically not straight, right? But we're just doing an approximation, so it's approximately straight. And so this is approximately a triangle. Okay, and this triangle has, its hypotenuse has length A, and this side here has length C of A. Also, it is a right triangle, so I can do that. And then the final thing I will leave you with as a hint is that this is also a right triangle, or this is also a right angle here, right? Because this line from the center of the Earth to the outside is exactly perpendicular to the tangent of the sphere here. So that's a 90-degree angle. And then finally, it might be worth extending this line out down to here, extending this here so that we have another triangle. Okay, so that's kind of the picture we have for the vertical cross section. And next we'll do one which actually I think is a little easier, potentially. When I've done this with groups in the past, some groups were able to solve the vertical one first, some were able to solve the horizontal one first, so I don't really know which one's easier. So horizontal cross section is going to tell us how the red line distorts under this projection. And so we're looking at a horizontal slice, so we're kind of looking down from up above here. So I'm going to draw a picture of the bird's eye view from the North Pole, from above the North Pole. So the horizontal cross section, maybe I'll move it to a new page here. Well, looking down from above, all I can see is basically the equator, or the edge outside of the cylinder. So this is the cylinder, which lies on the equator of the sphere. Okay, and then if I draw the center of the Earth right there. Okay, so I've got some latitude line, which from above just looks like a smaller circle within this outer circle, which is the equator. And actually, maybe I'll draw it in black. So I've got something like that. And one of the red edges lies exactly on this latitude line, so it looks like that. And then the projection now is just going straight from the center out, and you can see, like I said, that the red line gets larger under this projection. So if we call this side length B, and so that's the side on the spherical rectangle, and it gets projected to something of length C of B here. Okay. Now what else do we know? We know that this length here, this is just the radius r. It's the distance from the center of the Earth to the outside of the Earth. And what we don't know is we don't know this distance. I'm going to call it little r. Okay. And in this case, our goal is to calculate C of B in terms of, well, it's going to depend on B, it's going to depend on theta, maybe it depends on r. And I mean, also, it's going to depend on little r. But we don't want little r in our final formula of the total distortion of the area, because we want a formula which doesn't depend on which spherical rectangle we chose, right? And this distance, little r here, obviously depends on which rectangle we chose. So my hint to you is that, actually, let's say this is r. Again, it doesn't really matter whether we use the top or the bottom line. But my hint is, you can see from this that r should depend on theta. And so we should be able to remove the little r in our formula because it should depend on theta. So we should be able to replace it with something involving theta. Okay? And so if we can accomplish this goal of getting C of B in terms of B and getting C of A in terms of A, then, so I'll call this goal 2, this is goal 2, this is goal 1. So if we accomplish both of these, I claim that we can see how area gets distorted. Why? Well, the area of the spherical rectangle, the shape, the rectangular shape, rectangular-ish shape, there we go. Rectangular-ish shape we drew on the sphere is not quite, because it's not actually a rectangle, but it's approximately equal to A times B, right? The area of a rectangle is just height times width. And so approximately this is the area that we started with, whereas the area of the projection of this rectangle is the area of the rectangle in the cylinder. Well, that's actually exactly, not an approximation, it's exactly equal to C of A times C of B. Okay, and so your job is going to be to compare these two numbers, and if you believe my fact here, that this map preserves area, they should be the same. Okay, and like I said, this here is an approximation, but it becomes more and more accurate the smaller we make A and B. And so infinitesimally, when you replace this with like a dx dy, the infinitesimal area is going to be exactly exactly given by this number. And so that's how you would sort of rigorously prove that all areas are preserved, not just these rectangles and not just up to some approximation. Okay, I guess the final thing I want to say, which some of you may be wondering about, is we've seen cylindrical projections in real life. As like real life maps. So for instance, the Mercator projection. And as you probably learned in elementary school, this projection does not preserve area. In particular, it distorts things more and more the further you are from the equator. And that's why on that map, like Greenland looks really big, Antarctica looks larger than the rest of all the land masses combined, because you're distorting the closer you are towards the poles. So what's going on? We just proved that cylindrical projection preserves area, but we've been taught that Mercator projection does not. And the reason is that the Mercator projection is not the same as the one that we did. It's actually a different projection onto a cylinder. It's not the cylindrical projection. That we just defined above. In particular, by design, it basically starts out as this projection, but then the Mercator projection stretches things. So first you project on the cylinder in the usual way, and then you stretch the cylinder, kind of pulling the ends apart, and you stretch more the closer you are to the equator. And so that's where the distortion of the Mercator projection occurs. You might ask, why do that stretching if you're losing this nice property that the projection preserves area? And there's actually very good reasons for it. The Mercator projection has other nice properties, other things that are preserved by this map, which if you want to know more about, you can look on Wikipedia. Okay, so eventually you're going to have a homework problem, which is to prove this fact. And so I recommend trying to show these, accomplish these goals right now.